All right, let's get started. So today we're going to talk about Java EE programming, and we're going to continue along with JSP. So this is the introduction / everything you ever wanted to know about JSP. And we'll go through this. It's about 88 slides. So I'm going to talk for about an hour, hour and a half to 2 hours. Then we'll have lunch. We'll take a break after this. But if you have to use the restroom or something like that in between, go ahead and come back. You're not going to be rude, I should say. Because I guess people at home could pause the video and they can just sit there and go to the bathroom and come back. But you guys have to sit here and listen to it live. So, all right. It doesn't mean you can't watch the video later either. So, all right. So let's talk about JSP, Java Server Pages. Last time, if you weren't here, we did RMI, JDBC. We did UDP, TCP, IP. We did a lot of stuff already. So this is weekend number 2. And we've covered most of the stuff for the course, ending now with this weekend with JSP, Java Beans, Servlets, Servlet concepts, which is the focus of this weekend. So the focus of today, right now, is transaction management concepts. So basic concept of the transaction I'm going to cover. Also going to look at web tiering, servlets, Java Server Pages, which is on the menu for this morning. So without transactions, we don't have to worry about anything. It's just like the UDP TCP. You know, one client calls up to a server, requests something, sends something to the server, server sends something back. It's really just a two-way communication, and what we're looking at is just a protocol, which is UDP or TCP, just to transport information back and forth. When we start looking a little bit past that, we start looking at the concept of a transaction, and this is where JSP comes into place, and also the servlet concepts and some of the things under managed communication for the Java EE platform. So by definition, a transaction is a group of processes that either all succeed or they all fail. And when I say processes, I could mean processes in the terms of a Linux Unix process, or a task. Task is another word for it. So in terms of a transaction management system, or TM, is the mechanism for specifying, simplifying, and development of distributed multi-tiered enterprise applications that keep the transaction in mind. So they're transaction-aware communications. Standard service offered by J2EE platform by enforcing strict rules on an application's ability to access and update data. Transaction management ensures data integrity. So there's a lot of pros to this. There's also a lot of cons. You have to set this up and think about it ahead of time. But in terms of the pros, the Java 2 EE platform has facilities in there for transaction management, which is part of the tiering concept as well. So it means that the transaction management ensures that a unit of work either fully completes or it has no effect at all, and it's not going to leave garbage around. So it frees the programmer from dealing with the complex issues of data access, synchronized failures, failure recovery, and multi-user programming. So an example of a transaction-intense environment would be something along the lines of an ATM for a bank. So I'm going to use the ATM for a bank as an example as I'm going through the concept of transactions. And here's a picture actually of what it would look like. And you know, in terms of banking, that's probably the most critical application you can think of. If a transaction doesn't occur, you don't want it to partially complete. You know, like I withdrew money out of my account and I was ready to receive it through the ATM in the form of cash, and the ATM machine broke, or the power was lost or something. Most people would be extremely upset at the bank if they didn't get their money. And they walked into the bank and said, "Hey, we don't have any record of this. You didn't make any withdrawal. But half of it's out of my account already." You know, people would have problems with that. So in that particular case, if we were doing transaction management, we would make sure that all worked correctly before we actually committed the transaction, or actually, you know, dispense the cash or do anything. And that's one of the reasons why, actually, if you haven't noticed on ATM machines, it gets all the way down to the end, and it practically spits your card out before it gives you the money. Because it doesn't want to give you the money and then have a problem. Because, you know, obviously the ATM, the bank is watching out for themselves. You know, they don't care if you don't get your money. It's that if if you get money that you're not supposed to get is what the issue is. So they're going to make sure that the funds are deducted from your account and everything worked correctly before you actually get the money back, which is, you know, an order of the transaction. I mean, it's an order of the processing of the transaction. So here's you know, thinking about the order of the processing of the transactions, here's a scenario here where a customer enters a PIN, enters a card for the ATM goes to the bank, verifies, authenticates, come back, start a transaction, you know, select a withdrawal, select the account, select the amount. So if errors occur before this particular perform withdrawal, no problem. It's not that critical. But withdrawal completed, what happens if the network goes down here? Dispense the cash. Well, if you broke the link, it's not going to continue and dispense the cash out, essentially. Or it might dispense the cash out and then didn't update the account. That would be a problem for the bank. So, not to say that banks are only looking out for themselves, but, you know, I think about the concept. You want to make sure that it's done fairly, so you don't have to go back there and clean up the mess. So there's a lot of networking transactions out there that actually still fail at critical parts, and there isn't any, you know, I'm just going to say transaction garbage collection that occurs, or there isn't any, you know, cleanup that happens. Instead, you get, you know, have to call them up on the phone and say, hey, how come my account's locked? You know, well, that's because, you know, we had a bad transaction, we don't know what to do with this. You know, we have a floating something or other out there. So, and most people have heard of the acid test. If not, this is a little review of the concept because we are dealing with the concept of transactions. So it's not a bad idea to kind of think about in terms of good quality transactions. So the mnemonic to be used is acid. So remember these characteristics, and the acid stands for, the A stands for atomicity, C is consistency, isolation, durability, which gives us our acid. So what do these terms mean? And it's just like, you know, now you can use this all over the town. I'm going to give you the acid test. Oh, what do you mean by the acid test? You know, so it's a way of testing in terms of quality to make sure that your application is following, especially once you've designed it, these good transaction techniques. So atomicity, all of the distinct actions that appear to be a single atom or one unbreakable whole. So when you do a withdrawal from an ATM machine, it's like if we've seen in the previous slide here, a couple of different transactions going on, a couple of different tasks, I should say, that are part of this concept called the transaction. But this all seems to be one. You know, you put the card in, you put the PIN in, you select what you want to do. It gives us like it's all part of one. And what are we doing? Well, we're withdrawing cash, or we're using the ATM. So that the all succeed or the all fail notion exists, which is the first kind of quality that we want to ensure in the application development. And if any of the operations fail, then the transaction must fail and everything must be reverted backwards, which is, you know, not a bad thing to do in terms of fault recovery. Consistency. So a transaction must transition data from one consistent state to another, and preserving the data semantics and the referential integrity between the different states, also an important concept. So the system is a stable state before the transaction as well as after the transaction. So what we don't want to have is some system go through, perform something, and then figure out, oh, you know, now that we've corrupted the data, you know, now the before doesn't match the after and we can't reconcile. It's kind of like what happens when people's checkbooks get out of balance. There's no consistency in terms of what happened. And any temporary work or any transitory values are cleared away at the end of the transaction. Bookmarks, placeholders, locks on files, everything like that is cleaned up. It would be part of the consistency, which means you're retaining a consistent state from transaction to transaction. And one transaction doesn't make it so the next transaction is going to fail, or something of that nature. So in terms of the acid test, isolation, this transaction is isolated from all of the other transactions. This failure is isolated. Isolation means that the changes made to the data by a transaction are invisible to the other concurrent transactions that are occurring until the transaction commits. Isolation is kind of an interesting concept. Requires application design in terms of what's going on. In the old days, very, very, very long time ago, not possible today, but very, very long time ago, talking about ATMs again, you could get multiple ATM cards on the same account. Now, if you have noticed, if you have multiple cards, they have multiple different numbers on them. Because going back to the concept of a transaction and isolation, if you went, if you had two cards with the same number on the same account and you went to two different ATMs, you could simultaneously withdraw the same money twice without the bank knowing that, the money's not there for the second transaction. So let's say if you had $20 in the account and that's all you had in the account, you could, if you have isolation, which is occurring, and isolation does occur within the transactions, you could withdraw it. Now, the banks are pretty smart to that. Actually, that happened. If the timing was correct, you could do that. Now, each one of the cards has a different card number on it, so you can't mimic two simultaneous transactions. And not only that, but your account will be locked. So, if you've ever had a problem with an ATM machine, you probably have noticed that your account automatically gets locked anyway. So, kind of a security thing these days. But isolation basically makes it so they're living on an island of their own, and the transaction is going to occur regardless of what else is occurring at the same time. So hopefully it's not two withdrawals from the same account for the same amount at the same time. So anyway, it requires that several different concurrent transactions must produce the same result in the data as those of the transactions that would occur as if they were executed serially, one right after the other. So in reality, a system, whether it be an application server or a database, will be answering multiple requests in parallel simultaneously, and but they should be able to be serialized. So you should be able to go through and see which one happened first, which one happened second, third, and roll things back and fix things up, which is to be performed. So serialized means one is performed one at a time, queued up rather than assaulting the server all at once. So things actually do happen in serialized format, although they seem like they're happening parallel. So the theory behind it is the same transactions are fed to the server in the same order. It should reach the same ending state, hopefully, regardless of the order that those transactions occur. And that's the isolation part, the acid test. And then we have the D part, the durability. We committed the changes and they're permanent, and nothing is reversing it, and that the failures that occur after a commit cause no loss of damage or data, hopefully. So it implies that the data for all committed transactions can be recovered after a system or a media failure as well, in terms of the acid test. So transaction participants. So an application that uses transactions is called a transactional application. And so let's relate this back to Java EE for a minute. The transactional applications must consist of multiple servlets, JSP pages, and enterprise beans. So if you think of the concept of, and this is kind of a continuation of what I was talking about last time we met, about a month ago. Was it a month ago? I don't know. January? Oh yeah, it was a while ago. Okay, it was about a month ago. A little less than a month ago. And we were talking about the tiering, and we were talking about separating out responsibilities among different network components and the whole multi-tiering kind of environment. And I actually mentioned and talked about enterprise beans and the servlet components and the web server and the application server and the persistent server and all the little different pieces. Well, where it comes into play is when we start assembling these, we're thinking about the acid test and we're thinking about transactions as a concept. And so the transaction application consists of all of these multiple different servlets and all of these JSP pages and all of these enterprise beans that we're going to look at in this weekend's lecture, all working together to form the transaction, essentially. And so we can have a transaction manager that keeps track of all of these different components for us to let us know if something has failed, replace a component that has failed as an example, or reroute the traffic or do something interesting. So resource manager provides and enforces the acid transaction properties for specific data and specific operations that exist, and this would be referred to as the resource manager. It's kind of like the RMI that I talked about last time, the remote method invocation technique, that there is a register, and the register keeps track of all of the remote objects, and he's kind of like the transaction manager, but he's doing object brokering. He's not really doing transaction management. But if we think of the concept of the transaction manager and we implement that, then we can break out all the functionality into a bunch of different components and not worry about single failures. We don't have to do like error checking or communication back and forth between the different tiers. So an example of a resource manager might include a relational database which supports persistent storage and relational data, an EIS system, enterprise information system, managing transactions, perhaps external functionality and data, and then the Java message service, JMS provider, which manages transactional message delivery, which all work together in this platform to provide that ACID qualities. So the transaction application accesses a resource manager through a transaction resource object. So we create a transaction resource object to manage the transactions. And for example, a JDBC Java SQL connection object is used to access a relational database. And that's actually considered a lightweight transaction manager. And we looked at JDBC last time, and in our looking at it, I went over specifically a lot of the different features in terms of the methods for being able to make sure that the connection was good, the receiving of the result set was good, all of the different qualities associated with the connection that are examined and can be troubleshooted through the connection manager. And the connection manager is a resource manager / transaction manager, managing the transactions to the database. The connector is the resource adapter. So the connector is that driver, as we've seen so far. So the connector in the JDBC connector is the driver that is making the JDBC possible. So the connector is a resource adapter that has an API conforming to the Java connector architecture and the standard architecture for integrating the J2EE applications within EIS's enterprise systems. Enterprise information systems is what EIS stands for. So transactional programs must be able to start and end transactions and be able to indicate whether the data changes are to be made permanent or discard them. I'm saying it's pretty easy, doesn't it? So the idea is to automate it, and put some checks in there, and if the checks all work out, commit. If not, roll back. Use database terms for you. And so indicating transaction boundaries for a program is called the transaction demarcation. So transaction demarcation, another vocabulary, and a lot of this is what I'm giving you this morning is vocabulary that hopefully you'll be familiar with as we get through the day. So the boundaries is marking it, the demarcation. The program starts a transaction by executing a begin operation, and then we have an end at the end. The program then reads and modifies data with the scope of the new active transaction that's occurring. And then when the program is ready to make the changes permanent, it executes a commit operation. This would be from the database perspective, JDBC, causing the transaction to persist and any modified data to be committed, create during the active state to be saved. And that's why we actually refer to it as a persistent data tier or persistent tier, because that's what is going to exist after the transaction. It's going to stay the same. It's not going to, hopefully it's going to stay the same. It's not going to be corrupted after each one of the transactions that occurs. It's persistent data. So that's why the database tier is usually referred to as the persistence tier. So successful completion of the complete commit operation results in permanent changes to the transaction resource. So the transactional resource can be updated that things were successful, or if not, then things aren't going to be committed. So if a commit operation fails, for example, due to inadequate resources or data inconsistency violations or security checks, anything that would cause it to fail, the resource manager executes a rollback, discarding any changes that were made since the transition actually began or started. So the rollback would occur to undo anything. An application may also explicitly request a rollback during an active transaction if it can't complete it. So, in terms of the transaction itself, it's complicated by distributed computing, if you think about it. Going back to the tiering, if we distribute everything out over multiple tiers, which means we're putting them out on either logical or physical devices, then we have distributed transactions. If we're communicating, a persistent tier that's communicating with a Java Bean enterprise server that is communicating with a web server that's communicating with an application server, well, you've got distributed transactions that are distributed among all of the different components that are involved. So by definition, distributed enterprise systems often need to access and update multiple transactional resources in order to accomplish some business goal among the business tiering. And the distributed transactions are more complex than non-distributed ones, obviously, because you have the network failures and you have all the different components that are involved. If everything were all on one computer, we would not be having this lecture. What would it matter? If everything was in one program, it doesn't really matter. You just do some error checking on the program. But if we distributed it out all over the place, we might have things like transactions that become issues or they're more complex in terms of transactions because of the latency of the network, the potential failures, one or more resource managers becoming unavailable, interoperability concerns, lost connections, down servers, all sorts of different things that might happen. So on a network, a failed transaction can be difficult to distinguish from one that is merely slow, which is why a lot of things have timeouts in them. So if the database server doesn't respond within a certain amount of time, then you're going to come back and you're going to roll back something and you're not going to commit a withdrawal or something. So resource managers that do not know about each other cannot coordinate transactions or do anything themselves. So a transactional application could itself handle rollbacks, commit multiple different distributed resources, but only at a cost of a great deal of complexity, no reusable logic. So if everybody was thinking on their own, each one of these servers was basically a self-contained island of its own, and it was doing it, it would work just fine. However, there's no communication. You're taking away that distributed kind of transparency between the different computers. So a transaction context is the association of the transaction with the application component of the resource manager. It's referred to as the context of the transaction. And a transparent forwarding or a transaction content from one component to another or from one component to a resource manager is called a transaction content propagation. So we propagate the content of the transaction over multiple server units, or over multiple distributed parts. So let's talk about the transaction manager. So what I gave you up to this point is a lot of vocabulary, a lot of terminology. Some of you may have had it before from different contexts, but it all applies to the Java EE platform. And the center of it all is this transaction manager. And so the most common solution to the problem of coordinated distributed transaction is to introduce this third participant. Why is it a third participant? Well, it's not the application, it's not the data. It's the transaction manager who's the middleman between the application and the data. And he's making sure that things are in sync correctly, that your account was updated before the money was given to you from an ATM perspective. So the transaction manager acts as the mediator between the application and the multiple resources that the application uses, whether it be a database, whether it be a file server, network, other network components. And at any time during the distributed transaction, transaction manager maintains the association between each one of the transactions, has to keep track of how many simultaneous transactions are occurring. Which might be a unique global ID per transaction, transaction 1, 2, 3. Application threads that might exist, any connections to resource managers, and things of that nature. Here's what it looks like if you wanted a picture. A lot of people like pictures. This is kind of blurry a little bit, but I'm not quite sure why. The resolution is kind of bad on my boxes that are blown up. So this is the distributed transaction participants. Up here we have the transaction manager who is communicating with the resource manager. And then we have the transactional application itself. So the application goes to the transaction manager. And this is the demarcation. This is the transaction demarcation when it goes over and asks the transaction manager for something. And then we actually could ask the resource manager, are the resources available? Is anybody else using it? And then we have protocols that go back and forth between the transaction manager and the resource manager. So that's really the big picture of how the middleman, the transaction manager, actually kind of fits into the picture. So one of the things that from a primitive Unix perspective, and a lot of this actually kind of breaks down the Unix thread processing. Think of the concept multiple threads working together are sort of like multiple transactions working together. And if you had two transactions going on, actually this is the interesting thing. And if anyone's ever, actually I've never worked in banking, but I've heard so many stories about it. It usually lends itself as a good example. If you haven't noticed, like, you know, when you deposit and you withdraw, the deposit's always clear first and the withdrawal is always clear second. So, you know, because you can't spend money unless you have money, right? So, you know, at night when everything reconciles in the banking world, the withdrawals always go second, which is kind of interesting. Because if the withdrawals went first and the deposits went second, then you might over-withdraw your account. You might not have the funds available. So some of it is done in terms of a lock. So like say, for example, you have 5 withdrawals. And if you haven't, you know, actually, most banking still runs this way, actually. At night, everything reconciles. So during the day, all these transactions occur. And then at night, the computer accumulates and makes them all permanent, or rolls them back, or does something to make sure everything is consistent. Because even if you're off by a penny, if it's 1 million customers, you know, that's 1 million pennies. So that's a lot of money in the long run. So they need to be very accurate in terms of their transaction processing. So a lot of times things will lock. In fact, when you do a when you do a deposit during the day, it'll lock. You know, like, and then say, well, how come it doesn't? Well, it clears at midnight. You know, your account shows the money, but the money really isn't there because it has to wait to make sure that the person who gave you the money actually has the money to give you. So your check clears. So it's really a lock and a hold kind of mechanism, which is very similar to Unix processing. In Unix multi-threaded processing and inter-process communication, and using a lock and a mutex essentially. Which is going to end up happening. So databases are just like applications. You can lock a transaction, you can lock an update, you can commit an update, you can manage all of these different, and it's the business logic that somebody has to program into the application. It just doesn't happen on its own. So the usual solution is simultaneous access to shared resources, and the shared resource might be your bank account, is to employ a locking device called a lock in a database or a mutex in an operating system. A mutex and a lock are pretty much the same thing. One's from a Unix perspective, the other one's a database term. So the lock is a method for ensuring that only one process has exclusive privileges to change the state of a resource at a time, which means you have a mutual exclusion. You know, you've got a critical section of the program and only one thing is going to go in and touch it, which is what happens when you put your card into an ATM machine and you open up your account. Well, somebody else can't do the same thing anymore. It locks it. So you can't, you know, trick the system into thinking that, you know, taking the same money out twice or something. Should multiple requests require access to the same resource, such as a record of a customer's bank account, then only one is allowed to access the resource at a time. And then the, you know, it's one at a time kind of going in. It's a mutual exclusion, actually. Goes right back down to operating systems in terms of that concept. So here's an ATM example that we used before. When the verification of the account takes place, a lock is placed upon the particular row to ensure that it remains active as if it until the remains exactly the same until the transaction is completed. So nothing else in the background is going to come in and open it up and take funds out. So it's kind of like a read before write, you know. It wants to make sure the read value is correct. So at this time the customer account has been deleted. It would either fail or have to wait for the ATM process that would require the lock until the customer's account was opened up again and they were able to actually use it. So this wait would ensure that the account, if it was closed, the customer would receive only what was left in her account. Which means if you open it up twice and there's a lock on the first one, you can't withdraw the same money twice, essentially. You can't. And you know, when you think about the concept, banks are only concerned with you taking money that doesn't belong to you. So when you put money in, they don't really care how long it takes for that check to clear. They're going to lock it until, you know, they actually have their funds. So in terms of locking, the basic problem is that the lock is required for both reading and writing of a particular resource for consistency's sake. So if you read an item and it wasn't locked, something in the background might change the item. And then your read is out of date. And vice versa. The same thing actually true with the write. If you wrote something and somebody else had it open for read, their read isn't going to be updated with your write. So it's a reader-writer kind of issue or scenario. And it ensures consistency. So you could possibly imagine what the locks actually end up having in terms of a side effect. Well, it causes latency. Slows everything down if it's locked. So things have to wait. And if we have serial transactions going on, one right after the other, it makes our transactions process a lot slower. So although we want to maintain the transaction concept, we don't want to slow the system down completely. So in the second process, if the first process were to open up and read something, the second process were to read a row from a database while it was in use and being modified by somebody else, it might not receive the accurate value. And for lengthy transactions, any other process might have to wait until the read is actually a single value. Or, you know, wait until something has been returned or locked or released, I should say, before it can actually open it up. So locking issues doesn't scale well. If you have one resource and you have a lot of people using it, and forget it, it's too slow. So the concept of shadow pages is another choice. So in effect, the database makes a copy of the data that is undergoing change, and you're working on the copy, which is going to be the shadow copy, not the deep copy, in retrospect. So one copy of the data is the pre-transaction copy or the original copy, and then the other copy is the new copy, is the changed copy. So one copy is undergoing change. All of the read requests are forwarded to the pre-transaction copy, and then the changes can be merged. So it might be ignorant of any changes that are underway while other people are changing it. It's almost like when you take, actually this is a good example, if you take and you're in a company and you're all working on the same Word document and you pass the Word document around by email, everyone has a copy of it and people start making changes to it. Not like Google Docs or Google Docs, everybody's sharing one copy of it. So it's harder to reconcile all of the individual changes when everybody else has their own copy. So although nothing is locked, you can still work on it. The merging of the changes and the reconciliation of the transaction is a lot slower. So you got your choice. The banking system does a shadow copy. You know, you have a copy of what's current. The bank's got a copy of what's current. Other views of the system has a copy of what's current. At midnight, at the end of the night, when everything is merged together, that's when all the deposits come in first and the withdrawals come out second, and there's an order to this chaos in terms of the reconciliation, and they call it reconciliation to commit all of the transactions and put everything back together. And at the end of the day, in the morning, you got a balance, and the balance is your copy for the rest of that day. And then at night, the balance changes, and then depending upon what happens during the day. So should the second copy process decide to make its own changes, it will be locked. blocked by the lock and the shadow copy for the data that has to wait. So here's an example of the reader-writer scenario where you have writer number 1 and writer number 2 over here, reader number 1, reader number 2 over here, and assuming we have multiple transactions going on. Writer number 1 has a write request, goes to the resource manager. And what you're looking at in the middle is the middle man here, the resource manager. He says, I want to write something. And then the reader says, well, I want to read something. So he goes to the read, and it says, read fulfilled. Write privilege granted. So the lock was created. Now we have the write granted. And then the write command is given. And then, let's say reader number 2 comes over here and it requests. So another read request. And then the read request is fulfilled from a shadow copy. So it's taking a copy of whatever happens to be the current state of stuff from the resource. And while the block is waiting, it goes over here and says, well, write complete here. And the resource manager is just orchestrating the how serial everything is, and which transaction is occurring before another, and which copy of the current state of the data is actually delivered. So this is really just, this slide is really just showing you the job of the resource manager in terms of how it fits into the big picture. Now, instead of what we've been talking about is a one-phase kind of write, it's kind of a lock and a release, we can come up with a two-phase commit protocol where the resource manager does that do not know about don't know about each other, can't operate directly on distributed transactions if they're not aware about which everybody's doing. So transaction manager controls the transaction, indicates to a resource manager when and where to roll back or to commit based on the global state of the transaction. Transaction manager coordinates the transactions between the resource managers using a two-phase commit protocol. Basically 2 steps instead of 1 to commit it. Two-phase commit protocol provides the ACID property of transactions across multiple resources. So in the first phase of the two-phase commit, the transaction manager tells each resource to prepare to commit. I'm getting ready to change your data. So it comes in and says prepare. So perform all the operations for the commit and be ready either to make the change permanent or undo the changes. Meaning it takes everything it has and says, can I go ahead and apply these changes? And is it going to ruin the consistency or integrity of this resource? And that was the first request. And then the second request, after each resource manager responds, indicating whether or not to prepare the operation, whether or not it's going to be successful or not. Then in the second phase, if all prepared operations succeed, the transaction manager tells it to, okay, submit it. It's almost like doing a check first, which makes it the two-phase. So you go in and you ask the resource manager, can I make this change? And then the resource manager comes back and says, yeah, okay. And then you make the change. So it's 2 calls instead of 1. So just like make the change, make the change, make the change. Because what will end up happening, let's say if it comes back and says, no, you can't do that right now, because somebody else has the resource open, and then it'll stall. It'll take the transactions out of order. Because if you think about it, this is transaction processing. So if it has other transactions in a queue waiting and they're all asking, some of the other ones might be able to go first. As an example, the withdrawals and the deposits. If the withdrawal comes in, can I commit? Can I commit? The resource manager is going to say, no, we still got some deposits out there we need to reconcile. Otherwise, the end result isn't going to be right, perhaps. So, if we take the pluses and the minuses all together, we might end up charging the customer some overdraft fees because we considered all of their withdrawals before we considered any of their deposits. So, otherwise, a rollback, if a commit doesn't exist, a rollback is going to occur and indicates the transaction failed. Alright, so Java 2 EE platform transactions. Supports a combination of servlets and JSP pages accessing multiple enterprise beans within a single transaction. This is where it all fits in together. So each component may acquire multiple connections to multiple resource managers And the TE platform supports both programmatic and declarative transaction demarcation. So we can mark the component pieces as part of a particular transaction, check to see if they all worked, then commit or roll back depending upon what we're looking at. So the transaction management is transparent to the component and the application code. It's the resource manager in essence. So J2EE application server implements the necessary low-level transaction protocols, such as interactions between the transaction manager and resource managers and distributed two-phase commit protocol. So it does it for us, so we don't actually have to think of any of these manual concepts. And it requires only support for so-called flat transactions, which cannot have any children or nested transactions. And that's the interesting component. So a transaction is a transaction, but what if a transaction has a sub-transaction part of it? It's really hard to control sub-transactions. So if you break everything out into a flat level, it means everything is considered of an equal participant in the transaction. We don't have any subs, so we don't have any priorities for which ones need to go first or second or third. It's all on the same level. So here's an example of transactions across multiple resource managers. And you might think, well, what are the resource managers? Well, they might be the beans. So the following scenario illustrates the transaction that spans multiple resource managers. Here's our J2EE server. We have our client that connects, and then we have this transaction here. And the transaction could be the database, the name, service, the EIS, enterprise environment. We could have, and these are application servers perhaps, we have bean X, Y, and Z. So we create, and what is a bean? It's a Java program, and it rides on the server, and it acts like the transition manager. It's in charge of a particular resource. And we looked at this actually when we looked at JDBC already in terms of the database connectivity. If we have a bean out here, then the bean connects to the database. The bean is actually its responsibility in terms of the management of that resource is to manage not only the connection but the state of the database, any updates that are going on. And the client doesn't work directly with the database. Instead, the client goes to the bean or to a web server that goes to the bean that goes to the database. So we tier it off, and then we can make sure that we have the correct control over the resource. So client invokes a method on enterprise bean X. This is enterprise bean X. Client comes in, and let's say client, and this is where all these technologies fit together a little bit. Let's say this is an RMI connection. It could be. Or let's say it's on some other middleware. Doesn't really matter what it is. Client's coming in, and the client is requesting a service from bean X. Bean X accesses database A using a JDBC connection. That's what we've seen so far, actually, in terms of that connectivity. Actually, we used JDBC when we went directly to the database. We didn't go through a bean, but we could very well have made it go through a bean. Actually, we could create the JDBC connection on the bean, which is how it should work, and then our application just calls the remote object. That's the bean that goes and connects to the database. It uses the connector driver. So then the enterprise bean X calls a method on another enterprise bean Y, which sends the JMS message to some other system using the JMS service provider. JMS provider, message service provider. This was JMS, stands for Java Message Service. And I talked a little bit about that, I think, in the first weekend as well. And then enterprise bean Y then invokes a method on enterprise bean Z, which updates and returns some data from an external EIS system using a resource adapter that implements a J2E connector architecture. So bean X talking to bean Y, talking to bean Z, also talking this way. So the beans themselves are talking together. So the transaction manager of the Java 2 EE server coordinates activities with the three resource managers. So the resource managers are the beans that are managing the access to that resource, and then the transaction manager is the persistent is the tiering in terms of the servlet environment or the server that we have it all put on. And the server ensures that the database update by being X and the message transmission by being Y and the EIS operation performed by being Z are either all committed or they're rolled back if they don't work. So if we have a transaction manager that's watching over the whole system, then we can do the checks on the different resource managers. So, do you need it? Well, possibly. If you're going to make sure, if you're going to have distributed applications and distributed transactions occurring over multiple computers, you know, you're going to configure the environment to facilitate this type of communication, this type of tiering. Here's a transaction across Java 2 EE servers. So the products can distribute transactions across multiple application servers. So here's the client, and the client's going into one server, client's going into another server. So the difference here is instead of putting it all on one server, we have it on multiple servers. So we tiered it out, which just means we've separated it out. It's going to run pretty much the same in terms of its connectivity and involvement. The only thing different is we have multiple servers. So client invokes enterprise being X, which updates data in the enterprise information system on A. Oops. The enterprise information system here is controlled by being X, and then calls another enterprise being Y that's hosted on a different server. So being Y is on a different server. And then enterprise being Y performs a read-write access to enterprise being information system on number B. Oops. So being Y only controls B. So being Y is not going to touch A, and being X isn't going to touch B. It's all controlled by its own separate resource manager. And then when X invokes Y and the two servers cooperate and propagate the transaction context from X to Y, the transaction context propagation is transparent to the application code. And this is where those terms are coming into play now. The context propagation is transparent, which means we don't know that it's on two separate servers, and we don't know that these resources are out here, actually. We don't care, we just log into the server. So at the transaction commit time, the two servers use the distributed two-phase protocol to ensure that the two enterprise information systems are updated with a single transaction. So it's using a two-phase kind of protocol that says, hey, are we able to update? Yes. Okay. So here's where it fits in terms of the transaction technologies, part of the components. And no, you don't have to program in this for this class because you need, in order to actually do this, you're going to have to set up transactions and you're going to have to set up tiering. It's a huge project. You're not going to do this until you actually have, servers and you have applications on those servers and beans created. And it takes a lot of, you can't just mimic this on a computer. It's kind of a little bit more challenging than that. So, well, we're not going to implement it, but I'll definitely be showing you some of this API stuff. So the Java Transaction API performs the specifications defined in the overall transaction behavior. So it's the Transaction API. It's part of the EE, or short for GTA, Java Transaction API. Specifies, defines, and contracts between the application servers, the resource managers, and the transaction managers. So we configure the API to perform the transaction management between all of the different components. So it defines requirements for the transaction management and the runtime environment. So it specifies standard Java interfaces between a transaction manager and the distributed application participants that it's trying to coordinate, applications, application servers, resource managers. Defines the interfaces that will let the application servers, everybody else participate regardless of their implementations. So they all can be implemented using, well, it's all going to be in Java, but it's going to be in multiple different types of technologies. It's implementation independent. The transaction manager API is going to essentially be a blanket, actually act sort of like middleware to all of it. So in the transaction is managed and coordinated by this particular API, and it spans multiple components, enterprise information systems, and it propagates automatically between components to access components within the transactions themselves. And here's an example on the bottom of the screen. For example, a JTA transaction may comprise of a servlet or JSP page accessing multiple enterprise beans, some of which access one or more resource managers. So what exactly it's managing is unknown. I mean, it's not unknown, but it's not like a pre-configuration. It's not like RMI where we can load a registry, load a interface, load the objects, connect to the objects. It depends on what you're doing, actually. It depends on what you have loaded and what services and beans you're using as to what the transaction manager is actually going to be taking care of. So the GTA, the Java Transaction API, begins either explicitly in the code or implicitly by an enterprise Java Bean server. So it can be started automatically, or you can actually call it, make an instance of the object in your source code, and manually configure the object to take care of these transactions. And it's just basically managing. I mean, it's a manager. It's managing the different states of the applications. So the component can explicitly begin a JTA transaction using the interface. And here's the interface for it right here, Java X transaction. So the main benefit of using the transaction is the ability to combine multiple components of enterprise information system access into one single transaction with little programming effort. Actually, it's almost as much effort as JDBC, which is not very much effort. So the platform itself propagates transactions between multiple components and enterprise information systems with no additional programming effort, essentially. We just create an object and we call it the transaction object. Well, it is an object. It's going to be an instance of a transaction. And then we add components to the object, and the transaction can be managed. So client tier transactions, because we've been talking about so far server tier transactions. So the Java 2 EE platform does not require transaction support in applets and application clients. Though, like distributed transactions, Java 2 EE products might choose to provide this capability for added value. This is all done on the server, long story short. If you wanted to, no one uses applets anymore anyway, but back when applets were popular, if you wanted to, you had to manually incorporate the applet control into the transaction manager. It wasn't actually, something that was going to be provided automatically. So you manually connected it in terms of the support for the transaction. To ensure portability, applets, application clients should delegate transactional work to enterprise beans. Let them do it on the server, either directly or by way of the web tier. Make a bean function out of it. And bean function are just small little, I don't know why they call them beans. I guess because they're small little Java programs. They're just like Java applications, but they're beans. People get caught up on the terminology and they go, I don't know how to create a bean. Looks and acts like a regular Java program. It is a Java program. So it's called a bean because it's so small and it acts like a resource manager. It's the terminology. So web tier transaction guidelines. We know about the web tier from last time. Servlets and JSP pages in a two-tiered application can access enterprise information systems within the scope of the JTA transaction. And the servlets and the JSP pages support only programmatic transaction demarcation, meaning it's done inside of the source code for the programs, and it's done programmatically. There's no resource manager / transaction manager that is being supported outside of the Java programs themselves. A servlet or a JSP page can use the Java name, look at the JNDI to look up and I have some more information on that in a few minutes, to look up the user transaction object using a standard defined name, and that's going to be from the user transaction object, and then use the user transaction interface to demarcate the transactions. So we can look up the object, find it, and then use the object's transaction object functionality to create the demarcation. Here's an example. It illustrates the use of the JTA user transaction interface. What we're doing, we're just creating a user transaction object instance, UT, and it's going to be looking up from the Java naming system. Don't be concerned with the source code, and as I mentioned already, you don't have to program using this. For this course, we don't have any programs that require you to create a transaction manager. It would be kind of hard to come up with an assignment for it. So, Enterprise Java Bean Tier Transactions. Let's talk a little bit more about those beans. Enterprise beans offer two types of transaction demarcation: bean managed and container managed. So this gets kind of hairy after a while, but now we're familiar with the word bean. Hopefully, small Java program. You throw a bunch of beans in a coffee jar, coffee can, and that's a container. Holds all the beans, right? You know, who goes to the store and buys one Java bean at a time? Actually, you can buy one piece of coffee bean at a time. Kind of stupid. Usually you take a scoop and you get a lot of beans and you throw them in a plastic bag or something, and you get a container of beans, which is kind of like what you're doing in Java. This parallel is identical. Instead of having just one bean on an island of its own out there working with a JDBC server or something like that, we create containers of beans. We stick all the beans in the container, and then we have the container that we can wrap support around, load the container, unload the container, swap the container with another container, and then deal with the beans as a kind of a whole lot of beans all together instead of each bean individually, which is the same parallel as coffee beans actually. So we have container managed beans instead of bean managed beans. In a container managed transaction demarcation, we have 6 different transactions or attributes that can occur, whether it's required, requires new, not supported, supports, mandatory, and never. We have no container managed, it would be never. So the application component provider or the assembler specifies the type of transaction demarcation and the transaction attributes for the methods of the enterprise bean and the deployment descriptor. So the enterprise bean itself, in terms of the transaction demarcation, uses this API here, user transaction, the same one we saw before, part of transaction, interface to explicitly demark transaction boundaries. This is for the bean managed component. Session beans and message-driven beans can choose to use bean managed demarcation. And entity beans must always use container managed transaction demarcation. So entity beans are going to be a part of the servlet environment, and if you're going to load them all up together, then you're gonna put them in a container. So bean managed transactions, the following pseudocode illustrates the kind of fine-grained control that you can obtain with a bean managed transaction. By checking various different conditions, the pseudocode decides whether to stop or to start different transactions with business methods. So it's just going to look at it, an example, begin the transaction, update table A. If some condition exists, then commit the transaction. If not, don't do it. So what you're doing is you're creating these transaction objects to do checks. It's a way of cross-checking to make sure that updates have occurred correctly, failures did not occur. So enterprise bean using a JTA transaction. Here's a sample source code for it. We would commit, begin the user transaction object, which basically means start it, perform the transaction, the work that's going to be occurring, and then stop it. So imagine the bean running along. It's almost like no, I can't think of anything else like this. I was going to say it's almost like JUnit or unit testing, where you've got, if you're familiar with the concept, especially with Eclipse, you could load up test cases that are running and are being built simultaneously with your Java classes, and you can run them, and you can run the program simultaneously, sort of, but not really. Still manual. This is more automatic. So it's not really that good of a parallel, but it's very similar. The transaction bean is running along with the other bean. It's like multiple running objects simultaneously. So the user transaction interface is used the same way as the Java Enterprise Java Bean tier as in the web tier, except that the reference is to the interface is obtained by calling the context get user transaction instead of by way of the name lookup through the server. Alright, so the flip side of that, if we're not going to do it bean manage, we'll do a container manage transaction demarcation. And so that the messages have, the container manages the transaction boundaries of the enterprise bean. That uses a container managed approach. So the transaction or attributes of an enterprise bean method determines the method's transactional semantics, determines the behavior of the enterprise bean container must provide when the method is called. So the behavior that's supposed to occur upon method invocation, and transaction attributes are associated with the enterprise bean methods of the bean's deployment descriptor. So it's done per container. Just an example, with a new, if a method has a transaction attribute requires new, then the enterprise bean container begins the new transaction API transaction object every time this method is called and attempts to commit the transaction before the method returns, because it requires a new one, so it calls it, brings it up. So you're explicitly specifying when the bean is actually going to be used and what methods are actually going to be called. So the same transaction attribute can be specified for all of the different methods inside of the enterprise bean, or different attributes can be specified for each one of the methods of the beans. So you can customize it per bean, is what this is saying, inside of the container. So in the container managed demarcation, an enterprise bean has some control over the transaction. So as an example, the enterprise bean can choose to roll back a transaction stated by the container using the method set rollback only on the session context, entity context, or the message-driven context object. So the bean itself has a mind. It can think, and it can decide when it's going to roll back something. Benefits of using container managed transaction demarcation. Alright, so the benefits. The transaction behavior of the enterprise bean is specifically declarative instead of programmatically. So in the other bean managed, it was inside of the bean code. We're programming it in. In the container, we're doing it from the outside and just controlling multiple beans. So it frees the application component provider from writing transaction demarcation code in the component. We don't have to do it in the component. So it's less error prone because the container handles transaction demarcation automatically. So we don't have to explicitly call it. And it is easier to compose multiple enterprise beans to perform a certain task with specific transaction behavior. So an application assembler that understands the application can customize the transaction attributes and deployment descriptors without any code modification. So transaction attributes. And don't worry if it's starting to get a little dry. It does get dry. I might actually end in about 20 minutes, actually, because this slide set is 88 slides, and it's on slide number 39. So I'm only about halfway there. Problem with this is a lot of vocabulary and a lot of it's a lot of, what do they call it? Concepts without the practical seeing it. If I could show it to you, I would. The only problem is it requires so much resources. It's impossible. So a lot of theory is what this is. That's what I meant to say. So I'm going to try and make it as, I don't know, as less dry as I possibly can, but this is pretty dry material, I have to admit. So even I'm getting bored just listening to myself speak. So that's why I take little breaks to lighten it up a little bit. Okay. All right, back to boring stuff. Transaction attributes. I can kind of skip through some of this stuff too. What is a transaction attribute and more vocabulary? It's a value associated with the method of an enterprise bean that uses container managed transaction demarcation. Oy. Well, we got transaction demarcation, I hope, at this point. We got attributes and attributes. So it's just an attribute of the transaction. It's just something we're looking for. So a transaction attribute is defined for an enterprise bean method in the beans deployment descriptor, usually by an application component provider or an application assembler. Hey. Okay. The transaction attribute controls how the bean container demarcates the transaction. Okay, so we're just basically setting the blueprint, the template, the attributes, the information that we're going to be looking for per the bean activity, and we're giving it to the manager, transaction manager, from a container level. In most cases, all methods of the enterprise bean will have the same transaction attribute. Otherwise, you're really nitpicking if you go down with each method having a different transaction attribute. So here are some of the transaction attributes to put this into perspective, and some of the settings that are associated with it. Required. Well, we've actually seen required new a few minutes ago, but required uses the default transaction attribute to ensure that the methods are invoked within the transaction API transaction. Causes the enterprise bean to use existing transactional context if it exists, or to create one if it doesn't exist. Basically, it says it has to run with the transaction, the JTA, otherwise it's not going to run. It's required. Required new means a new instance of it. So used when the result of the method must be committed regardless of whether the caller's transaction succeeds. And then logging is a good example. Logging would basically tell us what's going on. Supports. Another attribute uses the method that used for methods that either do not change the database or update automatically, and it does not matter if the updates occur in a transaction. Okay. Mandatory, used when the method absolutely requires an existing transaction. Can't get away without it. Never. Used to ensure that your transactional client does not access methods that are not capable of participating in the transaction. Not supported. Used when the enterprise bean access resource manager that neither does not support external transaction demarcation or not supported by JTEE. Alright, so here's an example of some live source code for you. Not that this is going to be any less dry than the material itself, but here's the University Registrar session bean example. And if you remember when I was going over the RMI, we did the Ask the Registrar program, and the Ask the Registrar program was using an RMI routine, did not contain any transaction management, did not contain any bean technology, didn't do anything. So if we add a little bit more and put a session bean on there, the session bean is keeping track of the current transaction, and it is the session. It's actually the same thing that we use in terms of web programming, session content. Keeps track of environment variables, keeps track of the username, password, stuff like that. So we can get the university name up here, get the reference. We can start the transaction. If it fails, then we can throw an exception on the Java bean and say, hey, transaction failed. So here's what the source code actually sort of looks like if we put it together. Transaction, object up here, user transaction, create a new instance of this object, run the begin on the object, perform the transaction itself, and then we have transaction.commit, transaction.rollback if it didn't work. So it kind of puts the pieces of the material into perspective a little bit in terms of what it is you're doing. And imagine you're just building an object to keep track of the transaction, and you're committing and you're rolling back, essentially, just the same way as you would manually do it on a database in a database session. But usually the programmer itself has to, figure out how to do that. Usually when you're working with a database, you're manually typing in commit or rollback or something of that nature. Alright, so this is a really good stopping point actually, because the next part of this lecture is going to move on to web tiering and servlets. So what I just gave you was an overview of the Java Transaction API, which you do not have to implement. If you want some more information, I believe this list Actually, let me just test it real quick. Java transaction, architecture spec, it should bring it up. And it does. Look at that. So if you click on that link in the lecture, and you can come up here and you can read all about the transaction API, JTA. And more than you'll ever want to know about it. So don't necessarily be concerned with, let me see if I can get back to that lecture. Oops, wrong one. And don't be concerned with not knowing all the intricate details about this API. What you want to get out of this lecture, and the thing to remember, is the vocabulary. Because the vocabulary is pretty consistent among other technologies of the same sort. A transaction is a transaction. Demarcation is demarcation. Distributed systems always have the same issues associated with transactions. I mean, because you don't have a centralized point for the control. So in essence, what you're doing is creating a centralized point of control for all of the different pieces that are spread out all over the network. So I think it's not a bad idea to break for lunch, actually, because we're halfway through. When we come back, this is about 88 slides. I'll finish. This is part 1, end of part 1. When we come back, I'm going to start in with part 2, which is going to get into servlets. There is an assignment that you'll need to do on servlets. That is something that you can implement easily. Questions, comments, or concerns? No, a lot of you people just showed up. Let me stop this video.